Okay, let's finish off how much. Let's do some numbers, okay? In just a second. What we're going to do now, I mentioned that potential energy is associated with something called a conservative force versus a non-conservative force. More on that later. Conservative force, if it slows you down, it'll speed you back up if you let it. Non-conservative, if it slows you down, we'll give it back. Later, we'll talk about the potential energy function for the universal gravity force. And we'll talk about potential energy for electric force, Coulomb force it's called, atomic force. There's different potential energies. For now, we're going to focus on translational kinetic energy. We'll layer in rotations later. And potential energy due to gravity, really due to the force of gravity interaction between here, Earth, and whatever object you're looking at. So let's take a look at that. By the way, that's called, those two together are called mechanical energy. We'll get to that in a second. So let's do this. Let's explore some amounts. In order to explore amounts, you need to look at energy units. The energy units that we often use that are useful for mechanical, motion kind of things are the joules. As you know, a joule, 1 Newton times a meter. We'll explore why that is later. Now, a Newton is like MA. We know MA is not a force, but anyway, that's kilogram meter per second squared times a meter, kilogram meter squared per second squared. Always run those through so that eventually you get very fluent with those. Now that's a joule. So we'll explore how much is a joule. I mean, what is a joule? Can it kill me? What's a joule? If you look at the website physics.nist.gov, that's the National Institute for Standards and Technology, they are charged with really coming up with, as carefully as they can, with measurements that set the standards for what we mean by these amounts. So it's an important business, and it's probably a pretty fun job if you check that out. You see some interesting things that are confusing. So sometimes we can work with rough numbers, but sometimes it really, really matters to be picky if you're pushing certain subtle technologies. For instance, 1 joule, all right? 1 joule for mechanical stuff, but often for thermal stuff, we'll talk about calories. And you see, and I don't memorize this, but 1 calorie, IT, that's IT. What does that mean? That's the international table. You don't have to worry about that, okay? In the international table, 1 calorie is 4.1868 joules, or 4.19 if you can round it off that much, right? But then you'll see in chemistry courses, that physics we often use this, 4.19. In chemistry courses, you might be confused, like, wait, my chemistry says 1 calorie TH, which stands for thermochemical. So a different measurement process gives a slightly different conversion, doesn't it? 4.18400 joules you'll often see. So you might scratch your head, and you really should. Sometimes we'll use 4.19 and sometimes 4.18. In physics, generally 4.19 here. Now thinking though, realizing a calorie is more than a joule. It's about 4 joules. So that's not that bad. You know, a pound is about 4 newtons. So anyway, there's also British thermal units. The IT is 1055 point that, and the British thermal unit for the thermochemical process is slightly different. Again, don't sweat that. Don't even look at that again. I'm going to erase it. It's gone. Okay, fine. We're not even going to worry about this too much. You can even go like that, and you can work with that fine. For electric and atomic nuclear, this is important, that an electron volt, we'll see, is 1.602. We often just use that, or 1.60. 177. So these folks have been working hard to push that certainty, haven't they? Times 10 to the negative 19 joules. So, man, that is tiny, right? That's tiny. Compared to a ton of TNT, what we call the energy equivalent of a ton of TNT, that's 4.184. It kind of looks the same, right? But a very different number, times a billion joules. So energy can be a tiny bit for us, or a huge amount, but oftentimes we'll be working in joules. Great, let's explore this now. So you know this stuff, and you can always look that up and get familiar with it, and as you work, you should really get comfortable with it. So let's go over here and talk about kinetic energy. How much is a joule of kinetic energy? Things are moving around. Well, kinetic energy, as you know, is 1/2 mv squared, which v is the speed. No direction here. A liter of water has 1 kilogram of mass, so does 1 kilogram of this hooked object here. One kilogram. So a 1 meter per second would be kind of a slow walk. You know, usually if you're walking somewhere, you walk about 1.5 meters per second. Anyway, at a slow walk, so that squared is 1, times that is 1, times a half gives me half a joule. So this kind of going like, that's half a joule right there. That's half a joule. Something like that. Something there. All right, what if I do twice? So that's a pretty rapid walk, twice as fast. So if I double the speed, notice that this doubling gets squared, so it's 4 times as much. So there's 2 joules, right? So you walk around, you know, quickly, walk like that, or you just go like that, you know. There's 2 joules. Here, like 2 joules? Sure. There's 2 joules. Now 3 times, well again, the speed triples. So it isn't 3 times the energy. It's interesting. You get 3 squared, or 9 times the energy, 4.5 joules. So let's take a look at me. If I'm about 80 kilograms, and if I go on a slow walk, 1 meter per second, so we can put that in there. 1/2 of 80 is 40 times 1 squared. So that's about 40 joules. If I'm walking down the hallway slowly, that's 40 joules. If I jog at about 3 meters per second, then that's 9 times as much. So a person might have, you know, obviously 0. And of course, when I say 0, we know that I've got jiggling energy in my body and I'm glowing and all that stuff. When we talk about mechanical motion, I can go 40 joules. I can really quickly get up to 360 joules, right? And if I run 6 meters per second, that's pretty reasonable. 6 squared is 36. That's 1,440 joules. So now you know the range for someone walking slowly to running is on the order of 40 to 1,440, something like that, right? Fastest person can run at top speed faster than 10 meters per second, maybe 11. But 10 meters per second squared is 100, so that's easy. 100 times this, boom, you should check it. You get about 4,000 joules, right? So that's crazy. Why? Because that's 100 times as much as that. That's 4,000 joules. So now we get a person. Now what about a car? Mass of a car times 2,000 kilograms. Think about it, right? So 2,000 kilograms, that's kind of reasonable. 22 miles an hour is about 10 meters per second. So, you know, around town. And we do that. Now check this out. 1/2 m gives us the 1,000. So that's 10 to the 3. Times 10 squared is 100. So that's 10 to the 5 joules. Now, I erased that somehow. Oh, I know how. But remember, a number without units doesn't mean, I have no idea what that means, right? I could guess, but your job is to make it so we don't have to guess and waste our time. Okay? If you double the speed of that car, it doesn't go up, the energy doesn't go up by 2, it goes up by 2 squared, right? And if you triple it, of course, it goes up by 3 squared. So this is interesting. If you double 2 times the mass, then that doubles the kinetic energy. Here, versus 2 kilograms, doubles the kinetic energy. But doubling the speed makes it go up by a factor of 4. So in some sense, speed contributes more in some sense, right? So if you'd rather have a small thing going faster, in terms of factors, then of course you'd have to define exactly what you mean. You might get more energy out of it than a more massive thing going slower. All right, all things considered. So we can see that to get, if you want to talk about a joule, you know, that's like this, going maybe that fast. That's what a joule is, okay? Something like this. That's a joule of kinetic energy. I'd have to walk really slowly for me to have a joule of kinetic energy. Now let's go over here to potential energy. So now I'm thinking about potential energy, remember? Remember potential energy of gravity is the force of gravity times h, but this really doesn't have any physical meaning. You really have to define where you set h equals 0. Mass and height are both linear. That is, they are first power, right? So if you double 1, it doubles the energy. All right, so real quick check. 1 kilogram, 1 meter above some 0 point. So wherever 0 is that you choose, I go up, that's about a meter. So relative to this, I would have, let's see, m is 1, g is 9.8 meter per second squared, 1 meter, so I get 9.8 joules, right? There's 9.8 joules above here. Now watch this, magic. 0 joules, how much energy do I have? 0. How much energy? 9.8 joules. If I drop it on my foot, I can put the 0 down there. It's still going to feel the same no matter what I do with this, because the change will be the same. independent of where h equals 0. If I double the height, so from the ground, that's about 2 meters right there, somewhere in there, right? So from the ground, I get twice as much, or about 20. 10 centimeters, this is kind of fun. 10 centimeters are a fist, right? Above my 0 point. What's that? From there to there, or from a tabletop, 10 centimeters. Well, that's 0.1, right? So that's 0.1 of this, or 0.98. So that's about, ta-da, a joule. All right, so take a liter of soda, which is effectively water, and raise it up a little bit, drop it on your toe or your finger, and you've just experienced 1 joule of energy going to your finger. Not too much, right? What about me? So if I take me and I jump up 1 meter, right? Or I drop down 1 meter, some amount. Well, when I'm 1 meter above that h equals 0 point, then I've got how much? That's about 10, that's about 80. So, roughly 800 joules. So that's what 800, it's something, right? You wouldn't want someone dropping down on you from up here. You certainly want them to drop down you from up there, because what? That doubles it, and that's what, 1,600 joules? So you have a sense, right? So that's something like 1,600 joules, if I did that correctly, right? And that looks a lot like me running at top speed. So me dropping here, so which would you rather have? Would you like me to fall on you from here or run into you at top speed? I don't know. And then how exactly that hurts, well, that factors in too. So this gives you a sense of how much, and you should explore these sorts of things. 1 joule is a very, reasonable, small amount of energy. It's physical, and we work in terms of 100 joules and 1,000 joules and without any problem. So let's see. Let's finish this. A baseball coming at you at a certain speed, you can calculate that. That's kind of fun. Figure, I don't know, 1/3 of a kilogram is something like that. If I go over here, I have 2 objects over here, one with 1 kilogram, one with 1/2 kilogram, 500 grams, right? If I set their center of mass the same, we'll talk about that later soon, same amount of energy? No, this says half as much energy. Why? Because half as much ability to hurt me or to change something, to fall on something. Here I have, again down here, I've got 1,000 grams and 500 grams, or 1/2 kilogram. And moving along, the one with half as much mass has half as much ability to change things, right? So there's that. But the speed, that changes. And we've got springs. Springs, potential energy of gravity, kinetic energy of motion. Those are what we call mechanical energy, and that's what we're going to now start exploring. But don't take this too lightly. You need to make sure that you're writing units, you're looking at your significant figures, you have a sense of what's reasonable, because that really plays a big part in one's real work. So now we're going to do Energy Accounting 101. And play around with this. It'll be fun. Do a little bit of algebra. I'll set up a general equation. So next time.